All right, we've made it to the final lesson of the unit. So we're looking at modeling polynomial functions, and I will say that everything we've done up to this point is mostly just getting to this skill. This is the big one that we want. What we want to be able to do is take a look at a graph, and maybe it's a nice mathematical graph like this, or maybe it's just a bunch of data that we collected about some random thing, but something we want to find a model for, to come up with an equation for to represent it. So we've already seen how to basically deal with this. We know that there's a lot of important stuff about the x-intercepts when it comes to expressing the equation for the function in factored form. So if I take a look at this, I've labeled all the important points on here. I've labeled the three x-intercepts there, there, and there. So those are the three coordinates of the x-intercepts. I've also labeled on there the y-intercept, which we're not going to worry about right now. And then there's the local minimum and the local maximum, which basically means the bottom of that little trough on the left and the top of that little peak on the right. So they're not technically minimums and maximums. They're called local min and max, which means they're the biggest or smallest points in their general area. So we know that the general equation of this is going to be a some letter or some number times all of these little brackets, each of which is going to be x minus one of the x-intercepts. So the first x-intercept is minus 1, so this will be x minus negative 1 or x plus 1. And then the next one's at 1, so that's x minus 1. And the last one's x minus 2. So that's basically the equation. We just need to figure out what a is. Now I do know just by observation a little bit about a, and because this is a cubic function that starts high and ends low, I know it has to have a negative coefficient, so I know whatever a is, it'll be a negative number. But I just don't know what its exact value will be. So I'm just going to do this one a little bit by observation to kind of show you how it works, but we will calculate the a mathematically to show you that you can do that in all situations. What I'm going to do is just graph basically that function but without the a value. So just ignore the a, and then this function here, I'll just make a little note of it here. This is, I should call it something other than f at x because we've already used that. I'll call it g at x equals x plus 1, x minus 1, x minus 2. So the same three brackets as our f at x that we were given in the first picture. The only difference is this time I've just said a is 1, which is why this one starts low and ends high. And also the values have been switched around a little bit. They're not just negatives, they're actually different values. Now, one quick observation, and I apologize, I have to kind of keep scrolling back and forth here. If I go back to the original picture, I'm going to make a note that I have 3 points to work with. I've got this local minimum over here at negative 0.215, comma, negative 6.338. I've got the y-intercept at 0, comma, negative 6. And I've got the local maximum up here at 1.549, comma, 1.893. Now, of those 3 points, I think it's very safe to say that the nicest one to work with would be the y-intercept, 0, negative 6. Nice, simple numbers to work with. So that's what I'm going to focus on. I can pick technically any point other than the 3 x-intercepts, which have already been used in the equation. I can use any other point to figure out what a is going to be. But here, the y-intercept is 0, negative 6. And if I scroll down here, without an a in front, I notice that the y-intercept is 0, 2. So the question I would ask myself is, what do I have to multiply 2 by to get negative 6? And the answer, I think, is negative 3. It should just be that easy. Now, if you don't see it nicely, this will work again with any point, no matter how nasty the numbers are. But by observation, I think the answer is negative 3, because I want to get from 2 times something is negative 6. Okay, so the question there, how is it different from the graph that we want? We just said that verbally. I'm not going to write anything down there, but that's the idea. I want to get my graph from 2 to negative 6, so I multiply the whole thing by negative 3. All right, so here's what we're going to do. I'll just make the note here. We think a is going to be -3 just by observation. But what I'll do is I'll put down f at x equals a times x plus 1, x minus 1, x minus 2. And then if I want to find out what the a value is, I have to plug in, again, any other point from my original graph. So I can plug in x equals -0.215, y equals -6.338. It will work. It just will be really, really nasty because those are horrible numbers to work with. Pick a number other than the 3 x-intercepts that's nice. In this case, the nicest number I can see, or the nicest ordered pair I can see, is 0, -6. When x is 0, y is -6. So I'm going to plug that in. When I plug in 0, I get a 0 plus 1, 0 minus 1, 0 minus 2. So I've plugged in 0 for x, and f at 0 is -6. Inside these brackets, I can simplify them. That's just 1, -1, -2. -6 equals a times 1 times -1 times -2 is just +2. Finally, divide both sides by 2 and I get a equals -3. And that's it. If you can solve it by observation, by all means feel free to, but if you want to do something a little bit more concrete, you can always just plug in any ordered pair from the original graph, except the x-intercepts, which have already been used, and solve for a. That's it. Once you've got that, you can confidently say this function is -3 times x plus 1, x minus 1, x minus 2. There. We can do this with any polynomial function. I'm going to put a little asterisk on that. We do this with almost any polynomial function. There are some that are a little bit trickier to deal with. We're not going to worry about them in this course. It's something that if you ever do come into later, you can always worry about. There are some tricks you can learn to take this a little bit further. But for our purposes, it works anytime basically the graph keeps crossing the x-axis. If we ever have a situation where these little peaks or troughs occur entirely above or entirely below an axis. So for instance, if they look something like this, where this part here has no x-intercepts, no order 2 root, no order 3 root, then we have to use a slightly different method. And what we kind of do there, just to kind of give you a foreshadow should you ever see it, is we pretend that we redo where the where the x-axis is. So we move the x-axis up by, let's say, 5 or 10 units or whatever it is to make it cross a few points, and then bring it back down again. It's not perfect, but it's a good way of dealing with things. But don't worry, we're not going to encounter any of those in this course. All right, so here's what I'd like you to do. There's some practice problems. Now, this one here is just a straight up quadratic, but I'd like you to solve it like it's using this new polynomial method. And then we've got a couple others here. And I want you to make note that a few of them, like question 2, there's something special about this particular x-intercept here at -3. So you may want to pay attention to something special you need to do with that. And likewise, there's lots of special things going on in question 4. So give it a shot. Try them. The answers are at the bottom. You can always plug them into Desmos to double check to make sure that you're correct when it comes to whether or not your graph looks right. If you come up with the right equation, it should graph that equation or that graph in Desmos. You should be good. So give those a shot. If you got any problems, let me know. I will be happy to help. Otherwise, the next thing I guess we'll see you in is the unit test. Good luck.